We understand now that we have to think of at least three different kinds of particles when we're thinking about the numbers of states in a physical system. Specifically, first we have non-identical or classical particles, where we can have any number of particles in a given single particle state or mode. Second, we have identical bosons, where we can have any number of particles in a given single particle state or mode, but the particles are absolutely identical, which changes the counting of the number of possible states of the system available to us. Third, we can have identical fermions, for which there can only be 0 or 1 particle in a given single particle state, which also obviously greatly influences the number of possible states of the entire system available to us. These different behaviors of the different kinds of particles result in quite different kinds of thermal distributions. That is, at a given temperature, just what single particle states are occupied on the average by just how many particles. Understanding those thermal distributions is very important for a wide range of practical problems, everything from understanding the color of the sun to the operation of transistors. We will not attempt here to derive these distributions, though that is a straightforward activity when we combine our results so far with the standard techniques of statistical mechanics. But we will illustrate the different distributions for the different kinds of particles to show the consequences of the different behaviors of those particles. For non-identical particles, the distribution we end up using is called the Maxwell-Boltzmann distribution, and the formula for that is here. This PMB is the number of particles in a state of energy E on the average. And it's basically a negative exponential with Boltzmann's constant, Kb, times temperature on the bottom line and minus the energy on the top line. And we can also put in here another constant, here just called mu, which is an alternative to putting some normalizing constant out the front here. We would need a constant like that so that the total number of particles in some distribution would equal some specific number, for example. This term here actually has a name. It's called the chemical potential. And when we are dealing with one of the other distributions we will come to, called the Fermi-Dirac distribution, it's also known as the Fermi energy. But we can think of it as just a constant we have to put into the distribution so that when we look at some entire statistical mechanics problem, we get the right total number of particles. This distribution looks like the following, at least when we plot it up to 1 here. So we're plotting energy in energy minus the chemical potential in units of the Boltzmann constant times temperature. So this here would correspond to the energy equaling the chemical potential at 0 here. And we're plotting it up to plus 10 kb times T and down to minus 10 kb times T. In this case, this particular distribution would exceed 1 for all of these negative values here. For identical bosons, we get what's called the Bose-Einstein distribution. And here's the expression for that. And this expression here also has a chemical potential in it. You may often see the Bose-Einstein distribution plotted without any chemical potential. For the specific case of bosons like photons, the chemical potential actually is 0. And then this distribution is called the Planck distribution. Anyway, here's the form of this distribution. And here you see that for these positive energies, it rises and it keeps on rising. And it's rising faster as we go to smaller values here. It's rising faster than the Maxwell-Boltzmann distribution. For identical fermions, we get the Fermi-Dirac distribution. And here, explicitly, this mu is known as the Fermi energy. But this is exactly the same concept as chemical potential. And in this case, the probability, of course, cannot exceed 1. So we see this rises more slowly than both the Maxwell-Boltzmann and the Bose-Einstein distribution. And of course, it has to saturate at 1 here. So these are the thermal distribution functions that we use when we're trying to understand how many particles of a different kind are in which states of a system when we're working at finite temperature. And these are thermal average values. Note that for the identical bosons, they are more likely to be in the same state or mode than are classical or non-identical particles. That is, this blue curve here for the Bose-Einstein distribution is at all times higher than the Maxwell-Boltzmann curve. So identical bosons are more likely to be in the same mode than are classical or non-identical particles. The Bose-Einstein distribution lies above the Maxwell-Boltzmann distribution. For identical fermions, they are less likely to be in the same single particle state than are classical or non-identical particles. In fact, of course, they are never in the same single particle state. The Fermi-Dirac distribution lies below the Maxwell-Boltzmann distribution and the Bose-Einstein, and as I said before, it saturates up to 1 here.